Welcome to this presentation and demo dedicated to M4Mining's deliverable 4.2. As the project's work package 4 began in May 2023, it became clear that in order to complete our main objectives, namely providing a quick turnaround solution for hyperspectral imaging, data acquisition and processing on the one hand, and providing high-quality geological products on the other hand, we would have to develop both real-time and near real-time processing workflows. Here, we will focus on the near real-time processor part of the deliverable. You may be familiar with the concept of hyperspectral mosaic, historically the most common way of representing hyperspectral imaging data, typically obtained by geometrically transforming and merging individual push-broom scan lines into a single, spatially continuous image. With M4Mining, we no longer rely on mosaics, instead opting to harness the latest technological developments to work with hyperspectral point cloud data instead. Since our processing of hyperspectral data acquired by drone is based on a point cloud data representation, which is in itself a bit of a paradigm shift, we will first explain why using 3D point clouds helps our mission. Thereafter, we will restate the main objectives of the near real-time processor, which will also help us define what is meant by near real-time, before briefly comparing it with the real-time processor, which is also part of deliverable 4.2 and presented in a separate video. Then, an overview of the near real-time or NRT processor workflow will be given, followed by a demonstration of the software from data preparation to processing all the way to geological products. We will conclude with some example results derived from data acquired during M4Mining's latest field campaign in Greece in October 2024, which should drive home why we believe this automated end-to-end processor to be an extremely promising development for an integrated remote sensing approach accessible to the average end user for operational use at mining sites. The basic principle behind point cloud-based processing is that every spectrum of a data cube is tagged with its XYZ coordinates, and all subsequent processing is done in this structure, avoiding resampling and rectification. The main advantages of this approach are the preservation of original measurements, the fact that it works with arbitrary geometries. For example, we can now acquire data from vertical rock faces and even overhangs when doing horizontal view ray tracing. And moreover, this method reduces the amount of data to juggle with and ultimately results in faster processing times, all highly desirable for timely remote sensing operations. Now, the main disadvantage of this approach is how unfamiliar the results may seem at first. A priori, a 3D point cloud representation means no traditional reflectance mosaics. However, the NRT processor does allow the end user to optionally apply a georectification of the data should HSI mosaics still be desired. It is worth recalling that the M4Mining project takes a user-centric approach to development, aiming to develop an integrated remote sensing approach for mapping and monitoring active and inactive mining sites. One of the main goals of the M4Mining project is to develop an automated, high-precision workflow which allows to produce completely processed results within 4 hours of data acquisition for about 100 gigabytes of acquired data, much better than the typical days required for common airborne hyperspectral missions. Now, this integrated NRT processor has been designed for use with NEO's high-specs Mjolnir VS620 system, which uses 2 sensors to cover most of the solar reflected spectrum, that is to say, a wavelength range of 400 to 2500 nanometers. Now, the main outputs of this NRT processing are the following: radiometrically calibrated and geocoded hyperspectral data, full atmospheric correction for high-quality reflectance retrieval, and standardized geological products as a configurable option. At this point, it can be useful to compare the NRT processing capability with that of the real-time processor. The NRT processor provides fully physical, radiative transfer code-based HSI processing at full resolution for high-quality results, whereas real-time processing takes place directly on board the uncrewed aerial system, or UAS, and works with a reduced resolution to apply on-the-fly simplified atmospheric correction in order to retrieve preview classification maps. The NRT processing outputs absolute reflectance and provides a full suite of geological products. While the NRT processor workflow is complex, it can be understood as consisting of 5 main functional parts. The first is for raw data processes. In other words, the data preparation to be done before starting the NRT physical processing. Parametric geocoding with Reset Applications PARGE software. This is the main ray tracing routing with a digital surface model or DSM. The point cloud processes, which are specific to the point cloud-based hyperspectral processing in raw acquisition geometry. The drone atmospheric correction or DROACOR RESA software, which performs the atmospheric and topographic corrections for absolute reflectance retrieval. And finally, the production process, which consists of product generation as well as integration of flight line data into point clouds and optionally mosaics through rectification in order to obtain traditional raster map outputs. The entire processing workflow from raw data to product generation is automated, with the end user being simply given the option to configure some settings before starting the full processing of the HSI data. As already stated, before processing can begin, there is data preparation. After data acquisition, we recommend transferring the data to an SSD disk attached directly to the processing computer for faster processing times. The processor uses a strictly defined directory structure for both inputs and outputs. While the DSM mesh is typically obtained from LiDAR measurements, it is possible to import major external DSM formats, which can be useful if additional terrain information is required in areas not covered by the LiDAR DSM. The PARGE boresite status files and sensor model files for both sensors of the instrument are kept in the calibration subdirectory, and the processed navigation data, which contains the IMU and GPS information, are stored in the postpack subdirectory. This stage is also when the end user gets to configure a number of options before starting the actual processing. These more practical considerations will now be showcased in the demo.
Let me show you how this looks like. So you get your raw data. Your raw data has been sorted out in various ways, and once you have your raw imagery, this is the high specs data as it has been stored on the drone. Secondly, you got your ESM, which was created from the raw data in a filtering process. Furthermore, what you get is the processed Planix postback data. From within, you can read the IMU and GPS information, which has been optimized and corrected and filtered. So, as an further input, what you need is the boresite information, like this, and the sensor models for the 2 sensors. So these are the inputs required for the processing, and from there on, you should be able to start the process right away. The first thing is you have to select your main input directory, which is here the raw data, like that. And secondly, you get the digital surface model. You may have a look at this one to check if it's correct. And if you check it out, you will see you got this kind of a digital surface model, which is maybe still a little noisy, but this is what we get currently from the laser scanner. So this is the second input. And the third input, well, that's the definition of the output path. So I'm gonna write it to an output directory, and in there, everything will be sorted in various folders. That's in fact almost all to define. Well, there are some more things for the raw data import. You may have to define the location of the calibration information, like for the sensor model and the bore site. And you have to define the IMU and corrected IMU aspect file from postpack. So this is the configuration of the import. Further configurations are maybe in the first time you do it, the preferences. So where are your high specs pre-processing software packages like high specs thread and possibly high specs nav? This is the second input. So now that everything is configured, and you may start the process. So you can first maybe check the consistency. Well, it found 2 files in this data set, and so this can be processed. Apparently there is nothing missing, and one can go to the process. I won't start it because the raw data takes a while to be converted and is running in the background, but I can show you the output. So after the processing, what you get is an output directory. And inside the output directory, everything is sorted by the various subdirectories, like the reflectance, the radians, and then the geocoded radians and the products in the end. The log file, that's where I'm going to, are storing at first the configuration of the process, such that you can repeat it in a later stage and see what settings you have been giving. And secondly, you have the log file itself, which shows you how the process worked. So this is just an overview of the process I've been running on this small computer, and it shows you the high specs thread at first, and then the nav file creation, and afterwards it's going into the part geocoding and is processing the data to the IGM. So that's just the start of everything, and this will take on a small computer quite a while. On a recent computer, we are able to process everything, or this means about 100 gigabyte of original data in radians within the expected time frame of 4 hours from the start. This is the second part of the M4M processing system demonstration for deliverable 4.2. Well, let me show you how we get to really nice point clouds based on our processing system. So it will be about atmospheric correction and product generation with a link to the Breeze software from Predictera. Let me show this to you. So we are up with the processing system as shown before. And now we are showing how to process this Milos data from Breeze, this sample data set, which is the standard for our processing tests. So we're starting at the point where the import and the geocoding has already been done, and the processing system allows to redo the processing and start at any step in between. So this means you can start with the reflectance retrieval only and put it to, for instance, weak polishing and no removal. So that's the start point. Then you may put in the topographic correction. So we could have a topographic only correction, that's okay. Do some product generation as well. So the products we can use either internal speckle angle mapping, or use the USGS Mica system for the processing. So I'm gonna select that one. And if starting this part it will go through and it will finally maybe go into the product generation. For the product generation, you can already select, if it has been done before, a certain output, like the mica output, and save the options. So now I can start the process and it will go through the selected steps only and create new product. So we can start the process and it will go into the process like that and do all the processing right away. So the first data set is taken for spectral calibration, then it goes into the reflectance retrieval and it does the reflectance retrieval band by band for the 487 bands of the Mjolnir system. This was the first data set, then it goes into the second one and does it again. It will hence go into the third, and then we'll also do the topographic correction, and we'll see later how this looks like. So see, it's now doing the illumination correction. That's a fast process based on the digital surface model. The sky view factor and the slopes have been pre-calculated on the whole area, and such that you have a fast topographic correction done. Now it's going into the breeze correction. So it runs breeze runtime in the background. That's a geological classification algorithm with the USGS mica model. This was the first data set, which is going through, and it will go through all the three of them as well. So the breeze processing has finished, and a point cloud was created right away from all three processed data sets. This may be visualized now, either going to the NORSI software in a later stage, and currently you can also visualize this with the Cloud Compare. So for instance, I go to Cloud Compare and I want to show one of the products. I get some prepared mosaiced products. This means all three datasets have been put into one LAS file. First, I'm gonna load a shortwave infrared dataset, and this is shown in Cloud Compare like this. See the points here. That's a shortwave infrared display of the data. So the point cloud is clearly visible, so it's not a meshed data set yet. And you may also go to another one, so add one of the classifications. So I'm gonna load, for instance, the SAM classification, spectral angle mapper, like that one, which is a true color imagery. And this is now on top of the other one, so I can switch on, off, and see what's in between. Have a look at that, moving around, and see what happened to the data when doing the spectral angle mapping. So apparently there's still some information in the shaded areas, even though you can't see it in the visible display. So that will be one of our major focus in future activities, to see how much information can be retrieved after shading correction. So much about the outputs from the point cloud classification with our M4M processor.
Since producing geological maps of different surface materials, including minerals and rocks, is one of the most important geological applications, we will continue to add relevant hyperspectral image classification methods to the NRT processor in the coming months. In conclusion, we are now at a point where we have an automated end-to-end near real-time HSI data processor for high-quality reflectance retrieval and geological products. and simultaneously a companion real-time processor for preview classification maps. This brings us very close to an operational one-button solution for UAS-acquired HSI data processing, and all of this is strictly based on point cloud data representation, where the original spectra are preserved without the need for spatial resampling and thus avoiding processing overhead. During the next stage of development in 2025, quality control and validation of the outputs will become the main focus, notably within Work Package 6, and we will look into how automated data quality checks could be included before the physical processing to help the end user make informed decisions. Thank you for your attention.